Hello everyone and welcome to lecture 3 of Design and Analysis of Algorithms. Today we'll be diving into one of the most fundamental and powerful algorithm techniques, divide and conquer. So, um, divide and conquer is a strategy that has revolutionized the way we solve computational problems. It is widely used in designing efficient algorithms and plays a crucial role in many classic problem solving approaches, such as sorting, searching, and computational geometry. So, here is the introduction. um, So basically, it is a problem solving strategy that works by breaking a complex problem into smaller subproblems. Each of these subproblems is then solved independently, and finally, their solutions are combined to get the final result. So, this method follows a systematic approach. First, divide. So, break the problem into smaller, more manageable subproblems. Then, conquer. Solve each subproblem recursively or directly if they are small enough. Then, combine. Merge the results to obtain the final solution. So, why is divide and conquer important? Now, there are two key reasons why this strategy is widely used. First is efficiency. It provides a structured way of solving problems, leading to optimized algorithms with improved time complexity. Second is foundation of key algorithms. Like many well-known algorithms such as merge sort, quicksort, and binary search are built upon this approach, making it essential for any computer scientist or software developer to understand. So here is the breakdown that I just said, the steps involved. First, we'll break the problem into smaller, more manageable subproblems. These subproblems should ideally be similar in nature to the original problem. Then next we solve each subproblem. If the subproblems are still large, we apply the same divide and conquer approach recursively. So if they become simple enough, we solve them directly. And finally, we merge or combine the solutions of the subproblems to get the solution for the original problem. Now, this approach is widely used in various efficient algorithms. One of the best examples is merge sort, where an array is divided into smaller halves, sorted individually, and then merged back together in a sorted manner. Another example is binary search. So we'll also look at all the examples in our upcoming slides. Okay, so advantages of divide and conquer. We now understand the basic steps of divide and conquer, but why is this strategy so widely used? Let's see some major advantages. Um, First of all, it simplifies complex problems. One of the biggest advantages of divide and conquer, that is, it breaks down large and complex problems into smaller, more manageable subproblems. This makes solving them easier and more structured. Second is facilitates parallelism. Since each subproblem is independent, divide and conquer allows for parallel computing. This means that modern multi-core processors and distributed computing systems can solve subproblems simultaneously, significantly improving efficiency. Third is it solves certain problems optimally. So many fundamental algorithms such as merge sort, quicksort, and binary search use this approach because it provides optimal or near optimal solutions in many cases. For example, merge sort has a time complexity of big O n log n, which is much better than the big O n square complexity of simpler approaches like bubble sort. So next is it reduces time complexity. Well, in many cases, divide and conquer leads to more efficient algorithms. Instead of solving problems using a brute force approach, we recursively break them down, solving them faster when improved performance. So, because of these advantages, divide and conquer is one of the most powerful techniques in algorithm design. Okay, now we'll see some disadvantages. Um, um, it is so as it is a very popular algorithm, but it it also has some limitations. So first of all, overhead of recursion, like stack memory usage. What does it mean? So basically, divide and conquer often relies on recursion, um, which means that multiple recursive calls are made. Each function call consumes stack memory, and excessive recursion can lead to stack overflow issues if the depth of recursion is too large. Second is it may lead to redundant calculations. So some problems like computing Fibonacci numbers using a naive divide and conquer approach result in repeated calculations of the same subproblems. This inefficiency can be improved using techniques like memoization or dynamic programming. Okay, third is it not always the best approach for all problems. Like while divide and conquer works well for many algorithms, it is not always the most efficient choice. In some cases, an iterative or greedy approach may be more suitable, as recursion and the merging step may introduce unnecessary complexity. Now, despite these drawbacks, divide and conquer remains one of the most powerful techniques in algorithm design. The key is knowing when to apply it and when other strategies might be better suited for a given problem. Okay, like I said earlier, so these are some key algorithms which uses divide and conquer technique. Um, so these algorithms are widely used in computer science and demonstrate the power of breaking down complex problems into smaller, more manageable parts. So, first of all, is merge sort, quick sort, binary search, Strasson's matrix multiplication, closest pair of points problem. So let's go over one by one. Now here we have merge sort. First of all, so how merge sort works? First of all, we have three main steps here: divide, conquer, and combine. So this is how it uses the divide and conquer techniques in merge sort. First, we divide the given array into two halves until we reach individual elements. Then we recursively sort each half separately. Then we combine, we merge the two sorted halves back together in a sorted manner. So let's see an example. So we have this array 38, 27, 43, 3, 9, 82, 10. Now if we divide it, it will split into two halves. First half can have 38, 27, 43, the left side, and then the other half can have the right side elements starting from 3, 9, 82, 10. So we have now two halves. Now further divide until we get single elements. We can further divide it. We can have single arrays, like 38 could be one array, 27 is another individual one. So we can make it and break it down into individual arrays for each values. Then in concurred phase, sorting each half. So if we sort this, and we will have 27, 38, 43 in the left side half, and then on the right side half we will have 3, 9, 10 and 82. So we are sorting it in increment order. Now if we combine all of this and merging sorted halves, then we'll have 3, 9, 10, 27, 38, 43, 82. So we are just adding sorting after we are combining two halves and sorting the whole thing. Now time complexity. So since the array is always divided into two halves and merging takes linear time, the overall time complexity of merge sort is big O n log n, making it more efficient than many other sorting techniques like bubble sort. Okay, so now we'll see quicksort, which is also an efficient and widely used sorting algorithm. Unlike merge sort, which always divides the array into equal halves, quicksort works by selecting a pivot and then partitioning the array based on that pivot. So first of all, pick a pivot element. The pivot can be any element in the array. Common choices include the first element, last element, median, or a random element, anything. Then second, we'll partition the array around the pivot. Now elements smaller than the pivot so elements smaller than the pivot are moved to its left, and elements greater than the pivot are moved to its right. This is how we do the partition in quicksort. Then third, it recursively sort the subarrays. Now the process repeats recursively for the left and right subarrays until the entire array is sorted. So here we have this array 10, 80, 30, 90, 40, 50, 70. If we choose 50 as the pivot, so if we rearrange the elements around the pivot, we get 10, 30, 40, and then it is on the left side, and then on right side we'll get 90, 80, 70. I'll show you another example in diagram in upcoming slides, so don't worry if you don't understand here. So now we recursively apply the quicksort, and then on the left and right we have subarrays, and then after sorting those we'll have the final sorted array. Now the best and average case, we have big O n log n, the time complexity for it, which makes it one of the fastest sorting algorithms in practice. Quicksort is faster than merge sort in most real-world scenarios due to lower memory usage. It is an in-place sorting algorithm, meaning it does not require additional space like merge sort. Okay, binary search. Now, in binary search, it is used to find an element in a sorted array. Instead of searching through every element one by one, as we do in linear search, it continuously divides the search space in half, drastically reducing the number of comparisons. Now, the first step is divide. We split the search interval into two halves by finding the middle element. Then we check if the middle element is equal to the target value. If it matches, we have found the target. If the middle element is greater than the target, we repeat the search in the left half. If the middle element is smaller than the target, we repeat the search in the right half. Now then we'll continue this process until the target is found or the interval becomes empty. So for example, we have a sorted array 2, 3, 4, 10, 40. This is already sorted. It is on increment order from smaller to larger. Now suppose we are searching for the number 10. Now find the middle element. What is the middle element? If we say 0, if we add 0 and 4, and then divide it by 2, we'll have 2. So the middle element is 4. So 2 is the index. So we are first adding the index. So how many arrays is here? 1 2 3 4 5. 5 indexes. And array index start from 0. So on 0, array index 0 is the value is 2. Array index 1, the value is 3. Array index 3, array index 2, the value is 4. So 0 1 2 3, 0 1 2 3, 0 1 2 3 4. So it starts from 0 and it ends on 4. Total 5 values. So make sure you remember that, because array doesn't start from 1. You cannot count from 1 to 5. Index, the array address, index means the address of array. So the value 2 is in the index 0. The value 3 is in the index 1. The value 4 is in the index 2. The value 10 is in the index 3. And the value 40 is in index 4. So now if we want to search the middle one, then you will do a summation or add 2 and 40, which is the index are 0 and this index is 4. So 0 and 4. So we'll add 0 and 4, which is 4, and then we'll divide it by 2. That means 2. 2 is the middle element. And then 2, which address is 2? 4. We have 4 in the address 2, index 2. So 4 is the middle element we found. Now since 10 is greater than 4, we search in the right half. Here first we find the middle element, which is 4. Now we'll see 10 is greater than 4 or not. Since it is greater than 4, then we'll search the right half. So we're totally skipping the left half. So we totally skip the left part. So we saved some time. So instead of just searching from the beginning, it is already a sorted array. So that means whatever is the middle value, the right side values are always bigger than the middle value, and the left side values are always smaller than 4. That means 10, so if it is 10 is greater than 4, so we'll search on the right half, not the left half. Then we'll see we have 10 and 40, two values. And now find the middle of 10 and 40. If we try to find the middle of 10 and 40, the middle index is 3, and middle element is 10. So we got the match. The search is complete. Then the time complexity of binary search is big O1, best case, if the target is found immediately, and the worst and average case can be big O log n, as the search space halves each time. So binary search is much faster than linear search for large data sets. Like if you do the linear search, you have to start searching from 2, then you'll search 2, then next 3, next 4, next 10, and then you'll get the 10. But now on binary search, we just started from the middle element, which is 4, and then we went right, because the element we are searching is greater than 4. And it is widely used in applications requiring fast lookups such as databases and search engines. Okay, now let's discuss Strasson's matrix multiplication, an efficient algorithm that follows the divide and conquer approach to multiply two matrices faster than the conventional method. Now, here we have a problem statement. So matrix multiplication is a fundamental operation in various applications, including graphics processing, scientific computing, and machine learning. Now, the traditional approach for multiplying two n matrices has a time complexity of big O n cube, which becomes inefficient for large matrices. So, divide and conquer approach in Strasson's algorithm improves performance by breaking down matrix multiplication into smaller sub-problems. So first it divide the let's say we have the given n multiply n matrix is divided into four equal so n by 2 into n by 2 submatrices, quadrants. So then we have conquer. Instead of performing 8 multiplications like the conventional method, Strasson's algorithm uses only 7 recursive multiplication of submatrices. Then the computed results from the recursive steps are combined to form the final matrix. Now, this approach improves time complexity. So the traditional matrix multiplication takes big O n cube, and Strasson's algorithm reduces it to approximately big O n square 0.81, making it significantly faster for large matrices. Now, so we can say that Strasson's algorithm is an excellent example of how divide and conquer optimizes computational efficiency. It is widely used in high performance computing and applications that involve large scale matrix operations. However, for very small matrices, the overhead of recursive calls may outweigh the benefits. So it is often combined with classical methods. Okay, now let's see the closest pair of points problem, a fundamental problem in computational geometry that can be solved efficiently using the divide and conquer approach. Now the problem statement is given a set of points in a 2D plane, that the goal is to find the 2 points that are closest to each other. So a brute force approach would compare every pair of points, leading to a time complexity of big O n square, which is inefficient for large datasets. To improve this efficiency, we use a divide and conquer method with the following steps. So we will just first do divide. We'll sort the points by their x coordinates. I recursively divide the set of points into two equal halves by a vertical line. Then recursively find the closest pair in each half. This results in two minimum distances, d1 left side and d2 right side. The minimum of these two, d minimum, d1, d2 becomes our temporary closest distance. Then lastly, we'll combine, so some closest pairs may lie across the two halves near the dividing line. So we take only the points within distance d from the dividing line. And since the number of points in this strip is limited, this check runs in big O n time. So using the master theorem, this simplifies the big O n log n, a significant improvement over big O n square in the brute force method. So the closest pair of points algorithm demonstrates how divide and conquer optimizes geometric problems. And the key improvement is the stripe check, which prevents unnecessary computations. And this technique is widely used in computational geometry, computer graphics, and geographic information system. Okay, now that we have explored some of these algorithms, now take a step back and see the general pseudocode for the divide and conquer. So we'll try to understand the pseudocode of this algorithm. This is a high-level representation of how divide and conquer works for any problem. So we have function. So we'll go through step-by-step breakdown. first of all, base case check. Now, if the problem is small enough, return the solution directly. So on the function, we are starting from function divide and conquer problem. Inside the function, we have if base case equal to problem, it will just directly return the solution. For example, in merge sort, when an array has only one element, it is already sorted. Then divide the problem. So break the main problem into smaller subproblems of the same type, where we have divide problem into subproblems. This line means we are breaking the main problem into smaller subproblems of the same type. Then third, we are recursively solve subproblems. Solve each subproblem using the same divide and conquer approach. And then combine the solutions. After solving the subproblems, merge or combine the results to form the final solutions. So if you look at the pseudocode, for subproblem in subproblem, we have that solutions dot append divide and conquer subproblem and then return all combined solutions. So this is the step-by-step breakdown of the pseudocode. Now, how this applies to different algorithms. If we talk about merge sort, it split an array into two halves, sort them recursively, and merge them back. For quicksort, we have it picks a pivot, partitions the array, and recursively sort each partition. For binary search, it recursively searches the left or right half of a sorted array. For Stresson's algorithm, it splits matrices into quadrants and recursively multiplies them. So this is how each algorithm uses this general pseudocode. So this pseudocode provides a blueprint for implementing divide and conquer algorithm. And understanding this structure helps in designing new algorithms that follow this paradigm. So the key to efficiency is how well we define the base case, division, and combination steps. Okay, now we'll see the time complexity. So we'll analyze the time complexity of divide and conquer algorithms using the recurrence relation and the master theorem. So most divide and conquer algorithms follow a recurrence relation of the form T n a t n by b plus fn. This is the general recurrence relation. And where we have a is a number of subproblems, b is factor by which the problem size is reduced in each recursive step. Then fn is the additional cost outside the recursive calls. Then we have master theorem. The master theorem provides a straightforward way to analyze such recurrence relations and determine the time complexity. It consists of three cases. So on case 1, subproblem work dominates. So if fn grows slower than the recursive work, the complexity is determined by recursion, and the condition is d less than log ba. So the complexity is Tn equal to big O log big O n to the power log ba. So the example for case 1 is merge sort. So here if we say a equal to 2 and b equal to 2 and fn equal to big O n, we can say log 2 equal to 1 and complexity is big O n log n. For case 2, balanced growth, if fn and recursion grow at the same time, the complexity is slightly increased by a logarithm factor, and the condition is d is equal to log b, and the example is Stresson's matrix. Okay, so I will put these examples with details in the lecture, so it will be easy for you to understand. So third case is non-recursive work dominance. So if fn grows faster than the recursion, the overall complexity follows fn, and the condition is d is greater than log ba. And the example we had, then the dominant term is big O n square, making it the final complexity. So we'll see merge sort complexity step by step. So divide step, it takes big O1. In each recursion, the array is divided into two halves. Since splitting the array takes constant time, its complexity is big O1. Then on conquer step, it takes 2t n by 2. The problem is recursively divided into two sub-problems of size n by 2. Then on combined step, it is big O n. Once the sub-problems are sorted, we merge them back together and it takes big O n. And the final complexity is big O n log n. Then quick sort complexity. The divide base case is big O n log n, and then worst case is big O n to the power 2, and average case is big O n log n. I'll add those examples in details. So in this slide, we'll compare merge sort and quick sort, two of the most widely used divide and conquer sorting algorithms. So merge sort is stable sorting algorithm. This means it preserves the order of equal elements, making it useful for sorting data with multiple attributes. It requires extra space. Since merge sort uses an auxiliary array for merging, it requires additional memory, which can be a drawback for large data sets. But it has guaranteed big O n log n complexity, because merge sort performs consistently well with big O n log n complexity in all cases, making it ideal for large data sets where worst case performance matters. And in the other hand, in quick sort, it is an in-place sorting algorithm. That means, unlike merge sort, quick sort does not require extra memory, making it more memory efficient. But it can be unstable. That means quick sort does not guarantee stability, meaning equal elements may not maintain their original relative order. If we say that for performance, so merge sort it is good for large data sets, worst case guarantees, and quick sort is faster in practice with good pivot selection. So it has to be like a poor pivot selection can degrade performance to big O n square. So you have to choose the pivot, the value carefully. Okay, so we were talking about splitting and merging process for merge sort in divide and conquer. Now we'll see the visualization, so how it works. So the thing we were talking about up until now, we'll see it in this graph or visualization in this image. So here we have this same array 38, 27, 43, then 3, 9, 82, 10, and then we're splitting it into two halves on the second line, and then we're splitting it again, and then later we're splitting again, and then we're sorting it, and then we are merging it again, completing it again, and at the last we have the complete sorted algorithm, sorted array from 3 to 82, increasing order. And then we have the visual representation of quick sort also. Now here we are choosing the pivot. Initially the pivot is 8 is chosen from the array. Here if you look at this red one is the 8. It was the initial pivot, it was chosen, and now pivot moved to the end, and then we'll swap elements. So uh, the elements less than the pivot will be on left. So here we'll have 3 and then 2, then 4, and then 5 and 6. So now we have 3, 2, 4, 5, 6, 7, 8. So here after these swaps, all elements are smaller than 8 are grouped on the left side. So this is how quicksort works. Okay, now that we have explored all these divide and conquer, we'll see what are the applications for in real world problems. So first of all, how can we use this in real world problems? So we can first of all see we can use it to sort the large data sets, like algorithms like merge sort and quicksort. These are widely used in databases, financial transactions, and web applications to efficiently sort large amounts of data. For example, in e-commerce platform like Amazon, it sorts millions of products based on price, reviews, and relevance. Then we can search anything in database using binary search. So that will take that will be more fast lookups in sorted data sets. And for example, like search engines like Google use indexing and searching techniques that apply divide and conquer principles. Then third is computational geometry, like it is widely applied in geometric algorithms for problems like closest pair of points and convex hull. Convex hull is constructing the smallest convex boundary around a set of points. For example, GPS navigation and mapping systems use these algorithms to optimize routes and spatial data processing. So last one is image processing. So image compression algorithms such as JPEG, and wavelet transformation. These uses divide and conquer techniques to process large images efficiently. For example, if you like a fast Fourier transform (FFT) used in audio or image signal processing relies on breaking down signals into smaller components recursively. Okay, now we'll explore how the divide and conquer paradigm is leveraged in parallel computing, making it highly efficient for handling large scale computation. So many modern multi-core processors and distributed computing systems rely on parallelism to process large datasets efficiently. So the divide and conquer approach is inherently parallelizable because it breaks a large problem into smaller independent subproblems which can be processed simultaneously. So first we have task decomposition. The main problem is split into smaller independent subproblems. These subproblems can be processed concurrently on multiple cores. Then tasks are assigned to different CPU cores or GPUs, reducing computation time. And this is useful in supercomputing and cloud computing also. And then lastly, we'll combine once each core processes its assigned subproblem, results are merged efficiently. So for example, we'll see parallel merge sort is an example. So the splitting and merging phases are distributed across multiple threads, significantly improving sorting speed for large datasets. Another example is parallel matrix multiplication. So Stressen's algorithm can be parallelized by computing submatrix on different processors and merging results efficiently. Uh, so so these are the examples and steps we can use it on parallel computing. So Multi-core and distributed systems leverage this approach for tasks like sorting, numerical simulations, and AI computations. And it is a fundamental technique in high performance computing, enabling faster execution of complex algorithms. Okay, so we'll discuss divide and conquer in graph algorithms. So there are two examples like divide and conquer approach in finding connected components and applications in Kruskal and Prim's algorithm. And we'll now discuss Kruskal algorithm first, greedy approach. Now, what is Kruskal algorithm? It is an essential algorithm for finding the minimum spanning tree of a graph. Unlike divide and conquer algorithms, Kruskal's algorithm follows a greedy approach, making decisions step by step to ensure the best local choice leads to an optimal global solutions. So how this works? Kruskal's algorithm builds the minimum spanning tree by selecting edges in ascending order of weight while ensuring that no cycles are formed. First, it sort all edges in ascending order based on weight. Then it pick the smallest edge and check if it forms a cycle with the MST constructed so far. If it does not form a cycle, add it to the MST, and if it forms a cycle, discard it. And we'll repeat this step 2 until all vertices are connected. So the time complexity here sorting the edges takes big O E log E, where E is the number of edges. And using disjoint set union find operations takes big O E log V in total. So what is the use cases of Kruskal algorithm? First of all, it is used in designing computer networks, read networks, and power grids, where cost minimization is crucial. Connecting different cities with minimal road building cost could be an example for that. Second is clustering in machine learning. It helps in hierarchical clustering, where it connects the closest points first to form clusters. So image segmentation and pattern recognition could be an example for that. Okay, now we'll see Prim's algorithm here. It is also another fundamental algorithm for finding the minimum spanning tree of a graph. Like Kruskal algorithm, Prim's algorithm also follows a greedy approach, but it builds the MST differently by starting from a single vertex and growing the tree step by step. So instead of sorting edges like Kruskal algorithm, Prim's algorithm grows the MST dynamically by always adding the shortest available edge that connects to the tree. So we'll start with an arbitrary vertex as the initial MST. Find the smallest edge that connects a vertex inside the MST to a vertex outside the MST. Then add this edge to the MST and include the newly connected vertex. Repeat step 2 until all vertex are included in the MST. So basically it runs on big O V square time, which is inefficient for large graphs. And for priority queue, it runs on big O E log V time, making it significantly faster for sparse graphs. So what are the use cases? First of all, it also used in network design and wireless communication and routing algorithms to find minimum cost paths. And the second is graph based AI models, where AI pathfinding algorithms like those in robotic navigation, game development, and logistics So these are we can use it to find the shortest path for the delivery drones. So it could be an example. Okay, now we'll see a comparison between dynamic programming and divide and conquer. So first of all, divide and conquer basically breaks down the problem into independent subproblems, but in dynamic programming, it breaks problem into overlapping subproblems. And so in divide and conquer, there is no overlapping computation, and dynamic programming avoids redundant computation using storage. So and divide and conquer combines solution of subproblems at the end to get the final result, and dynamic programming uses previously computed solutions to get the final result. So the examples are merge sort, quick sort, binary search, and dynamic programming have Fibonacci series, knapsack algorithm, LCS. These are the examples for dynamic programming. And divide and conquer often follows master theorem for time simplicity, and dynamic program often reduces to big O n square or big O n. Okay, now we'll see some common pitfalls for divide and conquer. Um, so it has improper base case handling sometimes. It has redundant calculation due to lack of memoization and inefficient merging or combining step. It could be some common drawbacks in divide and conquer. Now we can say we can have some tips to make it better and for effective divide and conquer design. So the best practices are like we can choose an efficient dividing strategy first. So the way a problem is divided directly impacts the performance. So we have to be cautious to find and choose the efficient dividing strategy. Then we can optimize the combining step. So the efficiency of merging results affects the overall performance. So we can minimize the cost of recombining solutions by using efficient merging techniques. Then we can avoid overlapping subproblems. So if the same subproblems repeat, divide and conquer becomes inefficient due to redundant computation. So if you detect overlapping subproblems, switch to dynamic programming instead of pure divide and conquer. Okay, so now this is the last slide. So future trends here. So the applications in distributed systems, basically divide and conquer in the future will be more broadly used in distribution systems, and it will be used in AI and machine learning for large data to make it uh, easy to sort and make it do it faster. So that's the end of this lecture, and um, we'll have our lecture 4 in next week. Thank you.